Alright, let's talk about friction factors. So, a little bit of background. When people started to do experiments on flow regimes through pipes, they found that these variables were the variables that were the most important. So if they changed any of these from pressure drop, velocity, any of these, they saw differences in the outcome parameters, and they actually saw flow through pipes. So what exactly do I mean by that? Okay, one thing that was evident was that depending on certain flow regimes, depending on certain parameters that they actually fed through these pipes, the flow that came out was characterized differently. So the fluid properties of this over here are going to be much different than the fluid properties of this over here. And this flow pattern we would call turbulent, and this flow pattern we would call laminar. Laminar is typically a flow that's more well behaved. We'll talk about what that geometrically means in a little bit. And turbulent flow is not so well behaved. So the flow of the system, the velocity of fluid at certain points in here is it's more randomly arranged than in here in the laminar flow that you would see. Okay, so back to here. They knew that these variables were the ones that mattered the most. So what they did was they did what we did in the last lecture, is they tried to use the Buckingham Pi theorem. And they're like, all right, well, we'll choose velocity, inlet diameter, and density as our repeating groups, and we'll look at what happens for the remaining variables, just like we were doing before. So they chose the remaining variables being the pressure drop, length of the pipe, this E, which is actually the roughness of the pipe surface, and the viscosity. What they found when they went through this is the following. So they got these 4 pi groups. Remember, the pi groups are dimensionless groups, and one of the first things they did was they replaced this delta P over rho with head loss over G, and that got them this. So this is equivalent to this. Okay, so right off the bat, they called this parameter sort of the friction factor. The reason is because it deals with the roughness of the pipe and the diameter of the inlet. Now this fourth group over here is very special. This is what we call the very famous Reynolds number. So this quantity over here you should memorize. You might also see it in the form where this is a kinematic viscosity instead, where this viscosity down here and this velocity are combined into a new down over here. Okay, and if you remember your Buckingham Pi theorem, it says that you could write one pi group as a function of the other pi groups. So that's exactly what they did, and that looks something like this. So here we're writing this first pi group as a function of the remaining pi groups, with this proportionality constant here of phi 1. So from empirical studies, which means they just did a bunch of experiments and ran a bunch of numbers, they found that this L over D, this pi group number 2, is directly proportional to this. So this basically just means it's related to the other one by the first power and some sort of proportionality constant. So we're changing the constant from phi 1 to phi 2, but it's still an unknown proportionality constant, so that doesn't change too much. Okay, then basically what they say is, okay, multiply this v squared over g over to the other side, and then this unknown relation, so we don't know how exactly this is related to the left-hand side, but we're just going to call it some sort of factor, and what they call it here is the Darcy friction factor. So this transformation here is, we're saying these two pi groups, we know they're related to this pi group, but we don't know how, so we're just going to encompass it all in this variable called the Darcy friction factor. Now you'll also see people use something called the Fanning friction factor, and that's not too different. You'll just notice that it's the Darcy friction factor divided by a factor of 4. So this 2 out in the numerator goes to the denominator. So they're just related by the factor of 4. The factor of 2 over here, I don't believe it has too much significance. It's just kind of hanging out there. Okay, so what about this Fanning friction factor? So we know that it depends on the Reynolds number, and we know it depends on the roughness of the pipe. Okay, so the sort of problem there is that they started characterizing this Fanning friction factor, and the problem is it really depended on the regime of the flow going through the system. So if it was laminar flow in the system, it turned out to be somewhat well behaved. So it was pretty well related to the Reynolds number. The problem is when the flow is turbulent, they didn't find a good direct correlation. It wasn't as easy. So we'll see later that both of these are sort of encompassed in what we call a Moody table. And we'll work with the Moody table later. But basically the Moody table says that this friction factor is a function of both Reynolds number and pipe roughness. And it's either well behaved in the laminar region or not so well behaved in the turbulent region. So again, how do we know if something is laminar or turbulent? Well, that's a function of the Reynolds number. So depending on what your Reynolds number is, you're in a different regime. So a high Reynolds number typically means you're in a turbulent regime. And depending on how turbulent you are, you depend more or less on the Reynolds number. If you're extremely turbulent, then we pretty much have to use the Moody table, or the Moody chart, which you'll see in a bit. Notice that the Reynolds number depends on all of these factors. So again, the reason why we dimensionalize equations and we get these dimensionless groups is because they help us characterize the system. In this case, the Reynolds number lets us tell whether or not a flow geometry is going to be laminar or turbulent. And at certain points, when you're an engineer or a physicist solving these transport problems, usually you want to solve everything in variables and not worry about any of those constants. So if you're told the height's like 2 on one side and the height's 10 on the other side, you don't want to put those numbers into your equations until the very end, when you already have an algebraic solution. And then you'll plug the numbers in and you'll solve. But in general, you want to avoid doing that. You want a general solution to your problem. The difficulty is that there's certain things, flow pattern being one of them, that depend upon the actual parameters in your system. So they depend on the intrinsic velocity or viscosity or diameter of the inlet or density. And then you're stuck, unable to proceed with your general equation until you know more information about the system. Well, this allows you to basically, once you get to that fork in the road, you could say, let's solve the system assuming it's turbulent, or let's solve the system assuming it's laminar. And you could determine that from your input parameters, because you'll know your Reynolds number, and then be able to decide the flow type that you're dealing with. So again, you saw that graphic before I had. This one, I think, I just Googled it, looks even better at explaining sort of what everything looks like. So notice how in this laminar region, everything sort of parabolically tends toward the center. So you have the maximum velocity of the flow straight through the center of your pipe. And then on the edges, they're moving slower because there's viscous drag from the roughness of the pipe acting on there. Now when you have turbulence, you can't really have a function that characterizes your velocity profile as a function of the cross-sectional geometry. So all these slipstreams here are sort of random and not well characterized. So here you could see this is going the fastest, and toward the edge over here it's going a bit slower, whereas once you're turbulent it's just sort of an unpredictable mess. Alright, well that's enough theory for now. Let's actually try solving a problem. Okay, so the first thing I should say that these problems are incredibly similar to the energy problems we were solving earlier. This particular problem is from the University of Iowa, but I actually modified it because in that question you have to guess during one of their solutions. I didn't want to guess, so I put this pump in here. So the first thing we do when we're solving a problem that relates to energy, here we're trying to find the pump power, is we use that Bernoulli equation we figured out way back a few lectures. So the first thing I'm going to do is I'm going to throw up that Bernoulli equation right over here. So these factors you should be familiar with. What about these guys over here? Okay, well this HP is over here because the pump is helping push things along from, I guess, from here to here. It's kind of silly I put this pump here, but because there's no real, okay, well, just deal with it. But over here, this is what we're paying attention to. This H sub F is what is usually referred to as your major losses, and this sum of H sub M are your minor losses. So these major losses and minor losses are intrinsic to the system that you're looking at. Okay, and notice we're told that we have a roughness, well, we're told some parameters about the actual materials that were used to build the system. So in this case, commercial steel, we're told this factor here, and we're told the diameter of the piping here, and we're also told the viscosity. Okay, so the next thing to do is to write down what we know about both the locations that we're trying to conserve energy at. So for here, let me try moving this over first. Our point 1 will be over, oh, my bad. Give me 1 second. I don't think we'll actually have minor losses in this problem. Okay, so our 1 and 2 will actually look like this. My bad. And sorry for the fuzziness there. Okay, so notice that we're working with gauge pressure, which means we'll take this one and we'll say the other one's at atmospheric, so that one will be 0. So this is point 1. And we'll call this side point 2. Notice that we're in reservoirs, so the velocity is going to be 0 because there's no bulk velocity in either of these locations, and we're told that our height difference is, well, we're going to call this our 0 point, and we're going to say this is 15 off the 0 point. So that should all be straightforward. You should know how to do that from our energy video. So that will simplify to this. Okay, note that's basically just plugging in what we had before. I'm going to keep this P2 even though we know it's 200, and we have this head friction loss, which is our major loss, and we have this HP for the pump, which we're trying to find the power of. So if we rearrange things, we want to solve for everything in terms of HP. Well, that's going to start looking like this, but notice what happened here. So this is from our HF. So why does it look like this now? Well, I assume that our major losses can be characterized by this fanning friction factor over here, which we were talking about earlier. So this is just our fanning friction factor. Okay. Well, what do we need to solve for? We know this. We know this. We don't have a velocity. We're told, what does this L over D correspond to? It corresponds to this pipe region along here. So we're told the L and we're told the D. What we don't know is the velocity. But remember, the velocity we could get because we have the volumetric flow rate, which is Q, and we have the diameter of the pipe in that region, so that gets us our A. So we know our velocity, or we could get our velocity. We know L over D. What we don't know is this friction factor, and that's where this problem changes from the typical energy problems that we've been dealing with before. So I'm going to put this in here because we know that Q over A gives us our velocity. And now, remember, what was the friction factor depending on? Well, it depended on those two pi groups, the thickness or the roughness of the pipe over D and the Reynolds number. So those are the two things we need to find in this problem. And we're told originally that our roughness is given by this over here for this commercial steel, and we know the diameter. So we make sure the units are right there, and we get that number. Okay, what about our Reynolds number? Well, I told you to memorize what our Reynolds number was. It's our velocity times our diameter times our density over our viscosity. All those things are given. We had to figure this out, but we get our Reynolds number of around 149,700. So remember, our E over epsilon over D is about 0.0008, and our Reynolds number is about 150,000. So we need those to get our friction factor. And the way we get our friction factor is we have to use this Moody table over here. So this is a Moody chart. On the right-hand y-axis, you'll see the relative roughness, which is that pi group we were talking about before, that epsilon over D. And our Reynolds number is down here along the x-axis. So if you remember, our relative roughness was just about here. So we're going to be along this line. And if you look down here, you have your Reynolds number ranging from 10 to the third all the way up to 10 to the eighth. We are at 150,000. So that should get us, I believe, to 10 to the fifth is over here, and then we should be halfway in between. So if we go up, that should get us right about here. And we fall, oh god, sorry, let me do that again. That should get us right up to here, and then with a separate line, walk that over, and you'll see that our friction factor is just about 0.02. So to solve the problem, you would go back here, you'd say that the friction factor is 0.02, you'd plug that in right here, and then everything else you know. So to finish up, to find the power of that pump, you just say the power is going to be, if you remember from our energy video, just this, which is what it typically is. Alright, let's solve one more problem. So here, you'll see that there's a lot more things going on. So they're telling us a lot more information. They're telling us that there's a sharp entrance, an open globe valve, a bend, all these different parts. So these parts are the ones that will contribute to our minor losses. So we'll talk about that in a little bit. But remember, let's just go through our procedure. So first things first, set up our Bernoulli equation because we're dealing with energy once again. So that's going to look like this. Again, this HF over here is for our major losses. This sum of HM is for our minor losses, which we have now because we have all these small parts. And these are the listings of the minor losses. You'd have to look this up in a table if you're doing a problem. Luckily, this is an example problem from Frank White's book, so he attached all the K values, which we'll talk about in a bit, along with this problem. And we have a pump in here, so we know the pump's going to be supplying some sort of power. So once again, we need to write down what's going on at both the points of interest in our problem. So one I'm going to be calling over here, and 2 is going to be over here. Notice the first thing is that we have bars on both sides, so we know that the pressure is going to be atmospheric on both sides, so they cancel out. Now we're in reservoirs once again. V1 and V2 are going to be 0. Don't be confused by these going in and these coming out. We talked about that in our energy video. And we are given heights already. So this H1 and H2 are just from here. Okay, and let's simplify our Bernoulli equation with those. And that will get us this. So remember, we already know H1 and H2, and the problem is asking for compute the pump horsepower required. So once again, we're going to be looking for H sub P. Okay, so let's rearrange everything so that it solves for H sub P. Next, we need to figure out what this H sub F is, and we need to figure out what these H sub M are. So these are what they are. So once again, I'm going to assume that the major losses from the viscous drag along the pipe is going to be related to this Darcy friction factor from the beginning of this video that we figured out from dimensional analysis. This H sub M term over here corresponds to the minor losses. Notice it has this V squared over 2G, just like the major losses, but it also has this K to be substituted for this. This K depends on basically the part that you have on the system. So each of these Ks corresponds to each of these. So the sharp entrance is a K. The open glow valve has a K. All these have a K, and they're pretty much proportional to how much they create friction within the system and slow things down. So all these are going to depend on the same velocity, and that velocity is going to be the velocity through this pipe region here. And we're going to assume that's going to be the same throughout. So all of these are going to have the same V squared. Remember, we have many of these H sub M's, but since they have the same velocity, we can do the following distribution. So what I mean is, let's substitute from here to here, this here, the Darcy friction factor going in for H sub F, and the sum of the kV squared over 2G's for the minor losses. And then since I said they had the same velocity, we could distribute this V squared over 2G, and you'll see that we simply have to deal with this for the major losses and this for the minor losses. So we already know this sum of K because that's given here in this table. The only thing we have to worry about is this F, and we also have to worry about this V. So how do we get V? Well, the same way we got V last time, and it's going to be a constant velocity throughout this entire pipe section here. So notice we're told the diameter of the pipe, and we are told over here the volumetric flow rate. So we're going to do the volumetric flow rate divided by the area to get the velocity as usual. Notice so we have this diameter, and we also have this length. It's given by 400 feet of pipe. So the only thing we're really looking for, again, is this F. This is the only thing that's left in the problem that we don't have. How do we get the F? Well, same way as usual. We are told the density. We're told the kinematic viscosity. That's this nu here. And we're told our relative roughness. So since we have our relative roughness and we have enough parameters to find our Reynolds number, we can go to the Moody table. So the one thing I should have done is I should have calculated the Reynolds number, but know that it's simply going to be V times the diameter times rho divided by mu, and you're going to have to find mu because you're given a kinematic viscosity, I believe, not your regular viscosity. But once you find the Reynolds number and you're given the relative roughness, Then you do the same thing we did in the previous problem, where you go to this Moody table, you look at the right isotherm over here. Technically not isotherm, but you know what I'm talking about. You find the correct line over here, then you use your Reynolds number, walk up to the line, and then pull that over to the left, and that will get you your Darcy friction factor. And once you have your Darcy friction factor, you do the exact same thing as last time, and you solve for the horsepower.